Right now, on the eastern coast of Sicily, Europe's most active volcano is doing something that, according to everything scientists thought they understood about how volcanoes actually form and behave, should not be possible. Mount Etna has been erupting on and off for more than 500,000 years, throwing lava, ash, and incandescent rock into the sky so regularly that it has become one of the most closely monitored geological features on the entire planet. But a new scientific study, combined with a genuinely unusual pattern of activity happening at the mountain over the past several months, has revealed that Etna does not actually fit into any of the established categories scientists use to explain how volcanoes on Earth are built in the first place. It is reaching down to depths and tapping into a source of magma that, as far as anyone can tell, has never before been shown to fuel a volcano anywhere close to Etna's size. And at the same time, on the surface, the mountain has been producing a rapid, almost relentless sequence of eruptions, fissures, and ash emissions throughout 2026 that has kept the aviation warning level swinging between orange and red for months. Today, we are going to walk through both halves of this story, the deep scientific mystery just uncovered about where Etna's magma is actually coming from, and the very real, very current unrest playing out at the surface right now, and explain exactly why researchers are treating this as one of the more significant volcanological findings of the year. Before we get into the details, drop a comment and let me know if you have ever seen Etna in person or watched footage of it erupting, because this is a volcano that genuinely earns every bit of its reputation, and I want to hear what it looked like from the ground. And if breakdowns like this, real volcanic science explained without exaggeration, are something you want more of, go ahead and subscribe now. It costs nothing, and it means you catch the next update the moment this situation develops further, which, given everything we are about to walk through, seems very likely to happen. Let us start with the basic reason Etna has puzzled scientists for so long, because to understand why this new discovery is such a big deal, you first need to understand just how badly the mountain has resisted every previous attempt to explain it. For more than a century, geologists have organized nearly every volcano on the planet into one of three broad categories, based on the underlying mechanism that generates the magma in the first place. The first category covers volcanoes that form directly along the boundaries where two tectonic plates are pulling apart from each other, allowing mantle material to rise up and melt as pressure drops, the process responsible for building the ocean floor itself along mid-ocean ridges. The second category covers subduction zone volcanoes, which form where one tectonic plate dives beneath another, and where water carried down by the descending plate lowers the melting point of the surrounding mantle rock, generating the kind of explosive, cone-shaped volcanoes typified by Mount Fuji in Japan. The third category covers hotspot volcanoes, like the ones that built the Hawaiian island chain, which form over a stationary plume of unusually hot material rising from deep within the mantle, essentially burning through the crust above it, regardless of what the tectonic plates happen to be doing at the surface. Etna does not fit cleanly into any of these three boxes, and volcanologists have known this for a long time without ever being able to fully resolve it. Sicily does sit near a genuine subduction zone where the African tectonic plate is diving beneath the Eurasian plate, which is why Etna has often been loosely categorized as a subduction-related volcano in general reference. But the chemistry of Etna's lava does not match what a typical subduction zone volcano should produce, and the volcano's location relative to that subduction boundary is oddly positioned compared to other well-understood subduction volcanoes elsewhere in the world. Researchers have spent decades proposing alternative explanations, including the idea that Etna might sit above some kind of localized hotspot similar to Hawaii. But that explanation never fit particularly well either, since Etna lacks the kind of clean, long-lived volcanic trail across the surface that a true hotspot typically leaves behind as tectonic plates slowly drift over it. The honest state of the science, for a very long time, was that nobody had a fully satisfying answer for how one of the most studied, most active volcanoes on the planet actually came to exist in the first place. That changed earlier this year when a team of researchers led by geoscientist Sébastien Pillet at the University of Lausanne, working in collaboration with researchers at Italy's National Institute of Geophysics and Volcanology in Catania, published a study in the Journal of Geophysical Research that proposed something genuinely unexpected. The team collected and analyzed 85 rock samples spanning the entire volcanic history of eastern Sicily, tracing the chemical fingerprint of the lava all the way back to the late Miocene period, long before Etna itself existed in its current form, and continuing forward through the volcano's full 500,000-year history up to its most recent eruptions. What they found was that the chemical composition of Etna's magma has remained remarkably consistent across that entire enormous stretch of time, even as the surrounding tectonic environment shifted and changed dramatically. That consistency turned out to be the critical clue, because it meant the magma feeding Etna was not simply being freshly generated by whatever tectonic process happened to be active at any given moment, the way magma typically forms at subduction zones or spreading ridges. Instead, the evidence pointed toward something stranger, a large, pre-existing reservoir of partially molten material that has been sitting largely intact deep within the Earth for an extremely long time, periodically getting tapped and drawn upward to the surface. The specific mechanism the researchers landed on is called a petit-spot, a category of volcanism that most people, including most professional geologists, have never even heard of, because until now it had only ever been observed in a completely different context, and on a completely different scale. Petit-spot volcanoes were first identified back in 2006 by a team of Japanese geologists studying the seafloor off the coast of Japan. They represent a genuinely distinct way for magma to reach the surface. Rather than forming through the melting of fresh mantle material at a plate boundary, petit-spot volcanoes tap into a layer known as the low velocity zone, a partially molten region sitting at the top of the asthenosphere, roughly somewhere between 10 and 100 kilometers thick, depending on the specific location being studied, where seismic waves travel noticeably slower than they do through the surrounding solid rock, a signature that geophysicists interpret as evidence of small amounts of pre-existing partial melt trapped within the rock itself. In the areas off Japan where petit-spot volcanoes were first discovered, researchers found that as the descending oceanic plate bends and flexes on its way into a subduction zone, that flexing opens up small fractures, and magma from the low velocity zone gets squeezed upward through those fractures the same way water gets squeezed out of a sponge when you bend it, reaching the surface and forming small volcanic structures, typically rising no more than a few hundred meters, tiny by any volcanic standard. Here is where Etna genuinely breaks the established rules, because the study's authors are proposing that this exact same squeezing mechanism, extracting pre-existing melt from that low velocity zone, roughly 80 kilometers beneath the surface, may be the process responsible for building an enormous stratovolcano, one that rises more than 3,000 meters above sea level and has been continuously active for 500,000 years. Every previously documented petit-spot volcano on the planet has been a modest, comparatively insignificant feature. Lead researcher Sébastien Pillet described the finding directly, explaining that the process had previously only ever been observed generating very small volcanic structures, and that seeing evidence of the same fundamental mechanism apparently responsible for building something on the scale of Etna was genuinely unexpected. According to the model the team proposes, as the African plate continues its slow collision with the Eurasian plate, the resulting flexure in the crust beneath Sicily creates fractures that allow magma stored in that deep, low-velocity zone to migrate upward. In the earliest stages of Etna's formation, that rising magma reportedly interacted with silica-rich continental crust on its way up, producing the more viscous, chemically altered lavas found in the volcano's earliest deposits. Over time, the researchers suggest, the pathway to the surface effectively straightened out, allowing purer, more direct mantle-derived alkaline magma to reach the surface in greater volume, a shift reflected in the chemistry of Etna's more recent eruptions compared to its earliest ones. This discovery matters for reasons that go well beyond simply satisfying scientific curiosity about an old geological mystery, and it is worth being clear about why researchers are describing this as genuinely significant for volcanic hazard assessment, rather than just an academic footnote. Etna sits directly beside two major population centers, Catania and Messina, cities that together are home to hundreds of thousands of people living in close proximity to one of the most active volcanoes on Earth. Every model volcanologists use to forecast future eruptive behavior, to estimate how much magma might be available to erupt, how quickly it can rise to the surface, and how explosively it might behave once it gets there, depends heavily on correctly understanding where that magma is actually coming from and how it is being generated in the first place. If Etna has, for decades, been loosely modeled using assumptions borrowed from typical subduction zone volcanoes, and it turns out the mountain is instead being fed by an entirely different mechanism, drawing on a large, semi-permanent reservoir of pre-melted material sitting deep in the low-velocity zone rather than freshly generated subduction melt. That has real implications for how scientists estimate the volcano's long-term potential and how they interpret the signals it produces in the lead-up to future eruptions. Researchers involved in the study have been explicit that this reclassification offers valuable new insights specifically for assessing the hazards Etna poses to the communities living in its shadow, since understanding the true source and pathway of the magma is a foundational piece of being able to anticipate how the volcano might behave going forward. While that research was making its way through peer review and into publication, the volcano itself has been anything but quiet, and the pattern of activity throughout 2026 gives this whole story an added layer of urgency. The year opened with eruptive activity already underway at Etna's summit craters, with explosive activity concentrated mainly at the Voragine crater, and lava flows, actively advancing through the Valle del Bove, the large horseshoe-shaped depression on the volcano's eastern flank that has channeled countless lava flows throughout Etna's recorded history. By early January, observation teams tracking the flow field noted that the most advanced lava front had traveled more than 3 kilometers from its source, with the active portion of the flow spread across an area exceeding 500,000 square meters. That activity eventually cooled and stabilized, only for a new eruption to begin in late June, when a fracture opened near the base of the northeast crater at an elevation of roughly 3,000 meters, sending a slow but sustained lava flow toward the Valle del Leone, a valley on the volcano's upper flank, with volcanologists on the ground describing the flow as advancing steadily despite its high viscosity, continuing to emit volcanic gases and incandescent material from the fracture as it moved. Then, in early July, the situation escalated sharply. On July 5th, strong strombolian activity, a type of eruption characterized by rhythmic, relatively short bursts of lava and gas, began at Etna's summit craters, accompanied by intense ash emissions rising from a vent on the upper eastern flank of the Voragine crater. Within roughly 20 minutes of the activity intensifying, the eruptive cloud had climbed to about 1.5 kilometers above the summit, drifting toward the south and southeast, and Italy's Institute of Geophysics and Volcanology raised the aviation color code from orange all the way to red, the highest level on that warning scale, indicating an eruption is either underway or imminent, with a significant likelihood of substantial ash emission that poses a direct hazard to aircraft operating in the region. Observers on the mountain that day described the summit crater booming and emitting ash roughly every 3 minutes, and monitoring instruments recorded the average amplitude of volcanic tremor sitting within a high value range and continuing to trend upward even as the eruption played out. A second, similar eruption followed just over a week later, again originating from a fissure vent in the Valle del Leone area, with lava fronts moving past a landmark on the flank known as Monte Simone and descending into the Valle del Bove. What genuinely stands out to scientists monitoring this pattern is not just the frequency of these individual eruptions, since Etna has always erupted often, but what has been happening in the pauses between them. After the first major lava effusion in early July appeared to wind down, monitoring stations at the summit picked up small but clearly measurable shifts in the ground itself, roughly 0.3 of a microradian of tilt, recorded on a specialized instrument called a clinometer, alongside a measurable decompression signal picked up by an instrument known as a dilatometer, both changes occurring within a matter of hours. Instruments like these are designed to detect the extremely subtle physical deformation of the ground that occurs when magma is moving beneath the surface, even when that movement is not yet producing any visible eruption. INGV scientists interpreted these readings as clear evidence that magma continued shifting beneath the volcano even after the visible lava flow at the surface had technically ended, with renewed ash emissions beginning almost immediately afterward. In plain terms, the mountain was not resetting to a quiet baseline between eruptions the way it often has in past active periods. It was staying charged, with magma continuing to migrate somewhere in the plumbing system below, ready to feed the next episode with very little delay. This pattern of rapid, closely spaced eruptions with minimal recovery time in between is exactly the kind of behavior that keeps volcanologists paying extremely close attention, because it suggests a genuinely active, well-supplied magma system rather than a volcano working through the last remnants of a single, isolated eruptive episode. And now, layered directly on top of that pattern of surface unrest, sits the new understanding of where all of that magma is actually coming from in the first place. If Etna truly is drawing from a semi-permanent reservoir sitting in the low velocity zone, roughly 80 kilometers down, rather than relying on magma freshly generated through a conventional subduction process, that raises a genuinely open scientific question about just how large that underlying reservoir might be and how much magma could still be available to feed future activity over the coming years, decades, or centuries. Scientists studying Etna have been careful to describe this as a foundational reclassification rather than an imminent warning of catastrophe. But the honest scientific position is that a volcano behaving according to a mechanism previously observed only in tiny, obscure submarine features, now confirmed to be building one of Europe's largest and most active volcanoes, represents a genuine gap in previous understanding, and closing that gap is exactly the kind of work that directly improves the accuracy of hazard forecasting for the communities living closest to it. It helps to put this in historical perspective, because Etna's relationship with the people living around it did not begin with modern seismometers and satellite radar. It stretches back thousands of years, and some of the volcano's past eruptions offer a sobering reminder of what is genuinely at stake when a system this active and this well supplied with magma decides to send lava toward populated ground. The eruption of 1669 remains the most destructive in Etna's well-documented history, when lava flows advance steadily over roughly 4 months, ultimately reaching and partially destroying sections of the city of Catania itself. including breaching part of the city's defensive walls, displacing tens of thousands of residents in the process. In 1928, a much faster-moving lava flow completely destroyed the town of Mascali on the volcano's eastern flank in the span of about 2 days, an event still referenced today as one of the clearest demonstrations that while Etna's eruptions are usually slow enough to allow evacuation, they are not universally so, and the specific characteristics of any given eruption, its location, its effusion rate, and the terrain it flows across can dramatically change how much warning time residents actually get. These historical events are precisely why the modern monitoring network exists in the form it does today, built directly on the hard lessons of centuries of watching this particular mountain, and why researchers treat any meaningful shift in scientific understanding of Etna, including this new petit-spot finding, as something worth taking seriously rather than filing away as a purely academic curiosity. It is also worth spending a bit more time on the original 2006 discovery of petit-spot volcanoes, because understanding just how small and unassuming those first examples were makes the scale of what researchers are now proposing for Etna even more striking by comparison. When Japanese geologists first identified petit-spot volcanoes on the seafloor east of Japan, they were looking at tiny volcanic cones, some no larger than a few hundred meters across, scattered across the ocean floor in a region where the descending Pacific plate flexes as it begins its dive into a nearby subduction trench. These structures were so subtle and so different from the well-known volcanic arcs and hotspot chains geologists were already familiar with, that they had gone essentially unnoticed for years despite sitting in a region of the ocean that had already been mapped and studied extensively. What made them scientifically interesting was not their size, since by volcanic standards they are almost negligible, individual petit-spot volcanoes typically representing somewhere between 5,000ths and 1 cubic kilometer of erupted material, but the fact that they demonstrated an entirely new pathway by which the deep, low-velocity zone could directly feed surface volcanism, bypassing the more conventional processes geologists had spent decades cataloging. For nearly 2 decades after that initial discovery, petit-spot volcanism remained a niche, somewhat obscure corner of volcanology, relevant mainly to a small community of researchers studying seafloor tectonics. The idea that this same mechanism, scaled up by many orders of magnitude, might be responsible for constructing one of the largest and most consequential volcanoes in Europe represents a genuine conceptual leap, and it is exactly the kind of leap that tends to prompt other research groups to start re-examining volcanoes they had previously assumed were fully understood, rather than simply the first confirmed example of a broader pattern that might turn out to be common elsewhere. The specific combination of factors involved a slowly bending, actively subducting tectonic plate positioned in just the right configuration to fracture and tap into an unusually thick section of the low-velocity zone, sustained over hundreds of thousands of years with enough consistency to build a structure the size of Etna, is not a setup researchers have identified anywhere else on the planet. Other subduction zones exist all over the world, and other regions certainly have their own low-velocity zones sitting at similar depths. But the specific geometry that allows this squeezing mechanism to operate at the scale seen at Etna appears, based on current evidence, to be a genuinely rare coincidence of geological circumstances. That rarity is part of why the volcano has resisted easy classification for so long, and it is also part of why researchers are treating this finding as more than just a minor academic refinement. If Etna really is operating on a mechanism unlike any other well-documented volcano on the planet, then some of the assumptions baked into existing eruption forecasting models built primarily around the behavior of more conventional subduction zone and hotspot volcanoes, may need to be reconsidered specifically for Etna, since the underlying plumbing system feeding it appears to be genuinely different from the systems those models were originally designed around. Let us be clear about what this discovery does not mean, because with a headline this dramatic, it would be easy for the story to drift toward exaggeration. This is not evidence that Etna is on the verge of some unprecedented, catastrophic eruption, and it is not a signal that the volcano's fundamental danger level has suddenly and dramatically changed overnight. Etna has been one of the most active volcanoes on the planet for its entire recorded history, erupting multiple times almost every single year, and the communities living in Catania and Messina have coexisted with that reality for centuries, supported by one of the most sophisticated volcanic monitoring networks anywhere in the world. What has changed is not the volcano's behavior in some abrupt, alarming sense, but scientists' understanding of the underlying mechanism driving that behavior. And that kind of improved understanding is almost always a net positive for public safety, because it sharpens the tools researchers use to interpret the signals the volcano produces before and during future eruptions. A volcano that behaves according to a well-understood mechanism is, all else being equal, easier to monitor accurately and forecast reliably than one whose fundamental fuel source remains a mystery. And this new research moves Etna meaningfully closer to that first category. That said, it is genuinely fair to describe scientists as concerned in a measured and professional sense about what this combination of findings implies going forward. The persistent tremor, the ground deformation continuing to register between eruptions, the rapid cadence of strombolian activity and lava effusion throughout the middle of 2026, and now the confirmation that the volcano taps a deep, apparently substantial reservoir of pre-existing magma rather than relying purely on freshly generated melt, together paint a picture of a system that is well supplied and actively energized, not one that is running out of fuel or winding down toward a quieter period. Volcanologists at INGV have continued describing the volcano as remaining under close surveillance, language that reflects genuine active attentiveness rather than alarm, but it underscores that this is not a situation anyone studying the mountain considers settled or fully predictable. The honest scientific position sits exactly where you would expect it to for a volcano this complex, taking the new findings seriously as a meaningful update to decades of prior assumptions, while continuing to rely on the extensive, real-time monitoring network already in place to track exactly how the situation develops. That monitoring network itself deserves some explanation because it is a significant part of why a volcano this active, sitting directly beside major population centers, has managed to avoid the kind of catastrophic, unexpected disaster that has struck less well-monitored volcanoes elsewhere in the world. Etna is ringed by an extensive array of seismometers that continuously track the volcanic tremor generated by magma and gas moving through the plumbing system beneath the mountain, along with tiltmeters and dilatometers, the same category of instruments that picked up the subtle deformation signals following the July eruption, capable of detecting ground movement measured in fractions of a millimeter. Satellite radar interferometry adds another layer, allowing scientists to track broader deformation patterns across the volcano's entire flank from orbit, while thermal cameras and webcams provide continuous visual monitoring of the summit craters, even when weather conditions on the mountain make direct observation difficult. Infrasound sensors, which detect low-frequency sound waves generated by explosive activity, add yet another independent data stream, allowing researchers to track the intensity and frequency of eruptive bursts even during periods of poor visibility. Together, this network gives INGV scientists an unusually detailed, near real-time picture of what is happening beneath Etna at almost every moment, which is precisely why they were able to detect that continued magma movement within hours of the visible lava flow ending in early July, rather than only learning about it once a new eruption had already broken through the surface. This level of monitoring is part of a broader lesson that applies well beyond Etna specifically, which is that living safely alongside an active volcano is rarely about eliminating risk entirely, since that is simply not possible for communities situated this close to a genuinely active geological feature. It is instead about building the scientific and institutional capacity to detect changes as early as possible, interpret them accurately, and communicate clearly with the people who need to respond. Etna's long history of frequent, generally effusive rather than violently explosive eruptions has allowed authorities in Sicily to develop detailed evacuation and hazard zoning plans specifically tailored to the volcano's typical behavior, plans that get tested and refined essentially every time a new eruptive episode plays out. The relatively fluid, comparatively low viscosity nature of much of Etna's lava also means that in the vast majority of its eruptions, the primary hazard is not a sudden, unpredictable explosion, but a slower moving lava flow that, while capable of destroying infrastructure and agricultural land in its path, generally gives residents and authorities meaningful time to respond, evacuate, and in some documented cases, even attempt to redirect flows away from populated areas using engineered barriers. For residents and visitors alike, the practical guidance authorities in the region give is straightforward and worth repeating, because it applies just as much during a period of heightened activity like this one as it does during any other stretch of Etna's long, active history. Pay attention to the official aviation color code and any advisories issued by INGV, since those ratings are updated in near real time based directly on the same instrument network we just walked through, and they reflect the most current evidence-based assessment of what the volcano is actually doing at any given moment. Avoid restricted zones near active vents entirely, since ash emissions and sudden explosive bursts can occur with very little warning even during periods that otherwise look relatively calm, and never attempt to approach an active lava flow without an experienced local guide, given how quickly conditions on the mountain slopes can change and how difficult the terrain becomes to navigate safely, especially once visibility drops or darkness falls. For those living further away in Catania or Messina, staying informed through official channels rather than relying on secondhand social media reports remains the most reliable way to understand whether any given eruption poses a direct threat to populated areas, since the vast majority of Etna's eruptions, including nearly all of the activity recorded so far in 2026, have remained confined to the upper flanks and summit region, far from any residential areas. Stepping back from the day-to-day details of individual eruptions and instrument readings, what makes this Etna story genuinely compelling is the reminder it offers about how much remains unresolved, even about the volcanoes humanity has studied the most intensively. This is not some remote, poorly instrumented volcano in a location scientists rarely visit. Etna is arguably the single most closely monitored volcano on the entire planet, watched continuously by one of the most sophisticated observation networks anywhere in the world, studied by generations of volcanologists, and still, until earlier this year, its fundamental origin, the actual mechanism generating the magma that has built it up over 500,000 years, remained a genuine open question that no existing model could fully answer. That a team of researchers could look at 85 rock samples spanning that entire history and uncover evidence pointing toward a mechanism previously known only from tiny, obscure structures on the floor of the ocean off Japan is a striking demonstration of just how much subtlety remains hidden even within the most extensively studied geological features on Earth. It also reinforces something volcanologists have said for a long time in different contexts, that every individual volcano ultimately needs to be understood on its own terms, because broad categories and general models, however useful as a starting point, can only take you so far before a specific mountain reveals it has been playing by a slightly different set of rules the entire time. We will keep tracking this as it develops, both the ongoing surface activity at Etna, where eruptions have continued through the middle of 2026 with only brief pauses in between, and the broader scientific follow-up to this new petit-spot finding, since researchers are almost certainly going to be revisiting decades of prior Etna data with this new framework in mind, potentially uncovering even more detail about exactly how deep, how large, and how actively replenished this underlying magma reservoir really is. If breakdowns like this, real volcanic science explained clearly, without the exaggeration that so often surrounds stories about active volcanoes, are useful to you, make sure you are subscribed so you catch the next update the moment this situation shifts again. Drop a comment with your thoughts on whether Etna's unusual origin changes how you think about the risk it poses to the people living nearby, and if you know someone who has visited Sicily or has family living near Catania or Messina, send this their way so they have the real context behind what is happening at the mountain looming over their home. Some of the most active, most watched places on this entire planet can still surprise the scientists who have spent their entire careers studying them. And Etna, 500,000 years into its existence, has just proven that it still has secrets left to reveal.